Hi everyone and welcome to the internet. So what we're going to be doing in our lesson today is having a look at radiation in atoms. So to start us off, we've got 3 questions based around our previous lesson, so have a go at answering those 3 questions in your book. I'm going to give you about 4 minutes to do that. Let's mark those starter questions then. So our first one, we need to work out how many half-lives there are first of all. So if you did 25,800 divided by 5,700 and got the answer of 5, that's worth 1 mark for you. If we then worked out the fraction that means we've got of our activity, so a half times a half times a half times a half times a half, and we got 1 over 32, then that's worth a mark. But if you actually got the final answer of 890.625 becquerels, then you can just get all 3 marks for this. What we needed to do for that last step is just 1 over 32 times 2,500, our initial activity. So maximum of 3 for question 1. Question 2, we had to sketch the graph we'd expect for our half-life or the activity of our sample. So we start off up near the top, obviously on the left hand side, we've got a relatively steep curve and then it levels off to go out relatively gently towards the end. So if you've got something that looks like the graph in the middle of the screen there, give yourself a tick for that one. And then finally, our definition of half-life is the time it takes for the activity to decrease by 50%, or the time it takes for the activity to reduce by half. Something along those lines gets you your mark there. So add it up, we've got a maximum of 5 there, so give yourself a score out of 5. Before we go any further today, what we need to do is have a quick recap on some of those facts we've learned through our chemistry and our earlier physics lessons. So what I want you to do is draw me a diagram to show the structure of an atom with labels. Then I want you to say what charge a nucleus has and what charge electrons have. So I'm going to give you just over a couple of minutes to get that done. I'm hoping that we've got a diagram something like the one at the top of the screen there. So in the middle we've got our nucleus, which is made up of the neutrons and the protons, and then around that in those shells we've got the electrons. So give yourself a tick if you got the structure of the atom right. Hopefully we did say that the nucleus has a positive charge, because if we remember, the nucleus itself is made of protons and neutrons. Neutrons have no charge, protons have positive charge, therefore it will have a positive charge overall. And then finally our electrons have a -1 charge on each of them. So tick anything you got right there. So as we could see in that diagram of the atom, then our electrons actually occupy these certain energy levels or shells around the nucleus. Now, there was a scientist that actually came up with that part of the structure of the atom. See if you can remember who it is and write that in your book. Now, what we do know is that if we think about our work that we've done around the periodic table and the structure of atoms in our chemistry work, then what we find is, because we've got those different numbers of electron shells, then we've got different energy levels in those different atoms. So make sure you've got those 2 sentences written down, and hopefully write down the name of the scientist that made the discovery about the electrons occupying different energy levels around the nucleus. So I'll just leave that up there for about another minute. Hopefully we remembered that it was Niels Bohr who discovered this. So if you have Bohr, give yourself a tick. If we look at this diagram of our atom, we've got the shells going around as we're used to, and what we actually find is the one closest to the nucleus is the one with the lowest energy level. And obviously those energy levels are going to increase the further from the nucleus we go. And what we actually find is, if we think back to when we were drawing those structures of our atoms in our chemistry course, then we always start by filling the shell closest to the nucleus. The reason for this is that electrons usually occupy the lowest possible energy level. So that means they're going to be closest to the nucleus, but when that shell's full, obviously it has to go further away. So the lowest possible energy level are the ones closest to our nucleus, and those are the ones the electrons will occupy first and foremost. What we're going to look at now then is a certain model of how we're emitting and absorbing this radiation. So what we're going to look at is what's called the photon model. What we actually see here in the photon model is that this electromagnetic radiation that we've got in our atoms is going to be emitted and absorbed by them as these packets of energy, which we're going to refer to as a photon, hence photon model. Now, what we're going to find is that different photons actually have different amounts of energy associated with them. So the energy of each photon is actually proportional to its frequency. This will make a bit more sense as we go a little bit further with this, so make sure you've got those couple of points written down about the photon model first of all. I'll leave this up for about another minute so you got a chance to write that down. So, as we've said, in our atoms, then the electrons are normally occupying their lowest energy level they can. So they're trying to get as close to the nucleus as possible. What we will find is, as this electromagnetic radiation comes in and is absorbed by the atom, then the electrons will become excited. So what we refer to is we've got excited electrons. Now, when an electron is excited, it moves to a higher energy level. But in order to do this, then a photon of the right energy has to be absorbed. Now, once that photon has been absorbed, the electron moves to that higher energy level, and the whole atom is then in this excited state. And I've given you a little diagram at the bottom there that just shows you what's happening. So that line across the middle, okay, that's going to be our original energy level. Now, what we're going to find is it's going to absorb a photon, represented by the green arrow there pointing upwards, and that's then going to move that electron to the higher energy level, the next horizontal line that we can see. So we've moved that electron from close to the nucleus to a shell that's further away. So what we've done is we've moved it to a different energy level because it's got more energy as it's absorbed that photon. So the whole atom is now in an excited state. So I'll leave this up 30 seconds for you to jot down any points you haven't already got. If we imagine we've got some hydrogen gas, and what we're going to do is pass some light through that hydrogen gas. Now, the light that we're starting off with has got all the different frequencies. So if you think back to where we've looked at the actual spectrum of light, then we've got all those different frequencies from about 400 to over 700. And what we're going to find then is as that light passes through the hydrogen gas, some of those frequencies will be absorbed. So it will be those photons that give the right amount of energy to move an electron from one energy level to another. They're the ones that are going to be absorbed here. And what we will generate if we look at the light that's then coming out the other side of that hydrogen gas is something called an absorption spectrum. Now, I've shown you one at the bottom there for hydrogen, and what we can see is we've got our typical band of the colours going from our purples through the greens to the reds, but there are some vertical black lines on there. Now, those are showing the frequencies of radiation that have been absorbed by the hydrogen gas. Now, the reason that those ones are gone is because that was the amount of energy needed to excite those electrons to move them to the higher energy level. So what we've got are these very specific bands and patterns that we get for each element. So what we can see is by looking at this, just looking to see where those black lines are, we know that that's hydrogen that this light has passed through. So jot down those couple of sentences if you've not already, and then have a go answering the question at the bottom. How might this be useful to us? So I'll give you another minute with that on the screen. What we find then is that the largest energy difference that we could obtain is where we're moving an electron from the energy level just below that ionisation. So it's just below the energy needed to ionise the atom. Now, depending on what atom we've got, the amount of energy that is going to vary. Because if we think back to the work we've done on atomic structure in chemistry, then we know that different atoms have different numbers of those electron shells. So that means that the actual electrons are going to be able to move different distances in different elements. So for example, if we look at hydrogen, then that one can emit up to ultraviolet photons. But if we consider carbon, that one can emit X-ray photons. So there's a clear difference in the amount of energy that they've got available to play with, so to speak. So carbon will be able to emit up to X-ray, but hydrogen, because it's smaller, could only emit up to ultraviolet there. So again, jot those points down, just 30 more seconds if you've not got them. The last thing we really need to consider are our protons and neutrons. Now, I know that where we've drawn those diagrams of the atom, we just draw them like this blob in the centre. But actually, protons and neutrons will occupy energy levels within the nucleus itself, and therefore they can also see these changes. And when the protons and the neutrons are undergoing these changes, they can emit gamma rays because we're talking about much higher levels of energy being involved. So make sure that sentence is in your book. I'll just give you another 15 seconds if you've not got it already. So last thing for today is your plenary questions. So if your target grade is up to a grade 5, it's the 2 on the left. If your target grade is over a grade 5, the 2 columns on the right. So I'm going to leave this up here for about a minute and a half today, but if you need longer, as always, just hit pause on the video and take as much time as you need. As always, you can find the answers to the plenary over on my website, scienceright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.